In the late 1960s, the Cold War was being fought in the upper atmosphere. The United States suspected the Soviet Union might attempt secret nuclear weapons tests in outer space, away from ground-based sensors. After signing the Nuclear Test Ban Treaty in 1963, the U.S. launched the Vela satellites. These orbital watchdogs were equipped with sensors to detect specific gamma radiation pulses emitted by a nuclear detonation. On July 2, 1967, the satellites recorded a massive slash of gamma radiation. It was the exact type of energy the military was looking for, but the signature didn't match any known weapon. Scientists at the Los Alamos National Laboratory analyzed the arrival times of the signal across the satellite network. They determined the blast was not coming from Earth or the Sun, but from somewhere in the deep background of space. Military espionage had inadvertently revealed a massive, unexplained release of energy coming from the absolute depths of the universe, an invisible explosion that left no trace in visible light. For the next 3 decades, these events were impossible to pin down. Astronomers would detect a flash lasting only a few seconds, but by the time they pointed a telescope at the coordinates, the source had vanished. During this era, most researchers assumed these bursts were happening relatively close to home. They believed they were witnessing small, energetic events occurring within our own Milky Way galaxy. Data from the Batsy Observatory showed a different reality. If the bursts were in the Milky Way, they would cluster along the galactic plane. Instead, they scattered evenly across the sky, meaning they originated from galaxies billions of light-years away. If these flashes are visible across that much distance, they cannot be minor flares. We were witnessing explosions that release more energy in a few seconds than a typical star emits in its entire lifetime. The breakthrough came in 1997 with the Beppo-SAX satellite. It was fast enough to catch a burst and coordinate with ground telescopes to find its afterglow, the fading X-ray and optical light that lingers for days after the initial gamma-ray flash. By analyzing the spectrum of this fading light, scientists were finally able to calculate the redshift. This provided the first definitive measurement of how far the light had traveled through the expanding universe. The measurement was staggering. The burst had occurred 6 billion light-years away. A signal traveling that distance should be almost imperceptible by the time it reaches Earth. Yet the energy received was intense enough to be detected by relatively small satellite sensors. To be this bright from across the universe, these sources must release more energy in a few seconds than our Sun will in 10 billion years. They are the most luminous phenomena discovered since the Big Bang. Explaining that level of energy requires a model of total collapse. This is the collapsar theory, involving the death of a supermassive star that is spinning at high speeds. As the star exhausts its fuel, the core implodes into a black hole. The outer layers fall inward, swirling into a dense, high-speed accretion disk. This process generates twin relativistic jets. These plasma beams are driven outward at near light speed, punching through the dying star surface and into space. Short-duration bursts have a different origin, the merger of 2 neutron stars. When these incredibly dense objects collide, they form a black hole and trigger a similar, though shorter, release of energy. Their brightness relies on collimation. Unlike a spherical supernova, they focus energy into a narrow cone, maintaining intensity. We only detect a gamma-ray burst if Earth sits perfectly in the jet's path. Tilted slightly, it's completely invisible. These jets act as cosmic sniper rifles. The extreme brightness we record is not the result of a generic explosion, but of standing directly in the line of fire. Satellites now detect these bursts about once a day. Because they almost all occur in distant galaxies, they are harmless to us. However, the risk changes if a burst occurs within our own galaxy. If a star within a few thousand light-years collapsed and aimed its beam at Earth, the atmosphere would take the full force of that energy. The gamma rays wouldn't incinerate the planet instantly. Instead, they would cause nitrogen and oxygen in the air to react, creating a thick layer of nitrogen dioxide gas. This gas would deplete the ozone layer by as much as 75. Without ozone, the surface would be hit by lethal levels of solar UV radiation, while the atmosphere would wash out as acid rain. There is evidence that this may have already happened. Researchers believe a gamma-ray burst could be the cause of the late Ordovician mass extinction 450 million years ago. The fossil record shows a unique pattern from that era. Surface-dwelling creatures like these trilobites were devastated, while species living in deep water, where they were shielded from UV radiation, were much more likely to survive. Gamma-ray bursts are the most violent birth announcements in the universe. They remind us that the cosmos is a dynamic system, and that our survival depends on being a safe distance from its most energetic events.